There's a blind spot at the heart of modern computing that nobody questions anymore. For 70 years, every computer chip on Earth has been built on the same foundation: binary logic, just zeros and ones. We've accepted this as inevitable, as the only way computers could possibly work. But what if that was just a historical accident? What if computers didn't have to stop at 2 states? What if they could have 3? That's the radical idea behind ternary computing. And it's not just theoretical speculation. Decades ago, the Soviets actually built one, a working computer that operated on 3 logic states instead of 2. And today, this forgotten story is taking a very unexpected turn, as one of the world's largest tech companies just released a patent for a modern ternary chip. What you're about to discover challenges everything you thought you knew about how computers work, and suggests that the entire 70-year history of computing might have taken the wrong path. The promise that sounds too good to be true. Right now, training massive neural networks costs millions of dollars in electricity bills. Data centers are pushing power grids to their absolute limits. Artificial intelligence is burning through energy like there's no tomorrow. And once again, computing is hitting a fundamental wall, the same wall that Soviet engineers recognized in the 1950s. Binary logic might simply not be enough anymore, and with advanced chip manufacturing techniques and new semiconductor materials now available, 3-state logic might finally have its moment. Here's what makes this genuinely exciting. Huawei just released a patent showing their new ternary chip built at 7-nanometer scale. According to their patent documentation, this chip used 40% fewer devices, consumed 60% less power, and ran 20% faster than equivalent binary designs. Those numbers sound almost too good to be true. Cutting power consumption by more than half while simultaneously increasing speed, that's the kind of breakthrough that could transform computing entirely. In a data center environment, that could mean reducing energy costs by 1/3 while boosting throughput. For AI training specifically, that could slash multi-million-dollar power bills while accelerating development cycles. But here's the thing about patents. They're tricky. Whatever you patent becomes publicly available information. That's why the biggest breakthroughs often never get patented at all, which means there could be significantly more happening behind the scenes that we haven't seen yet. And that possibility is genuinely exciting. The biggest promise of 3-state logic is efficiency at scale. But to understand why this matters and why it's taken 70 years to revisit this idea, we need to go back to where it all began. The Moscow State University engineer who saw things differently. Imagine the Soviet Union in the 1950s. They'd had a strong start in computing. They'd built one of Europe's first digital computers and soon after released the BESM-1, a machine that actually outpaced America's best computer at the time, UNIVAC-1. But this triumph didn't last, and here's the real reason why. In the United States, IBM was manufacturing computers by the thousands using mass production techniques. Meanwhile, in the USSR, every machine was essentially handmade, assembled with scarce components and no economies of scale whatsoever. At Moscow State University, an engineer named Nikolai Brusentsov and his small team faced a brutal reality. Binary mainframes were prohibitively expensive, sealed inside government laboratories. Academic researchers couldn't access them. Students couldn't learn on them. The technology remained locked away from the people who needed it most. That's when Brusentsov made a radical choice. He would fight back by building an entirely new kind of computer, one simple enough to construct with the limited scraps available, cheap enough that students could finally get hands-on experience with actual computing hardware. Brusentsov spent months searching for a new approach. Then he met Sergei Sobolev, a brilliant mathematician who introduced him to ternary mathematics, a numerical system built not on 2 states but 3. This moment was like discovering color television while everyone else was still watching black and white. Suddenly, there was an entire new dimension to explore. Together, they began investigating how this elegant mathematical idea could be transformed into functioning computer hardware. Brusentsov argued something radical, that binary logic was purely a historical accident. Relays and vacuum tubes naturally had only 2 stable states, on or off. That's how 0 and 1 logic became the default foundation for computing. And since then, nobody had seriously questioned whether that was actually optimal, but Brusentsov and his team did question it. They started working on Setun, what would become the world's first computer to run on 3 logic states, -1 for no, +1 for yes, and 0 for something in between, a sort of maybe or neutral state. How 3 states changes everything. Imagine that each bit, now called a trit in ternary systems, can represent 3 states instead of 2. That means more information can be processed in each computing step. Mathematical operations can be completed with fewer moves. Even negative numbers don't require an additional sign bit, making subtraction and addition naturally simpler. Brusentsov realized this elegant mathematics could translate into circuits that were simpler, more efficient, and far cheaper to manufacture than binary equivalents. After 2 years of relentless work, in 1958 they finally unveiled Setun, the world's first ternary computer. Production began the following year at the Kazan Mathematical Machines factory. The hardware was primitive by today's standards, just 2,000 magnetic elements and 100 germanium transistors. But here's the remarkable part. Setun operated on very few components and cost at least 10 times less than binary machines of that era. According to research papers from the period, Setun used approximately 30% fewer parts than equivalent binary machines. It was radical, unconventional, and it actually worked. In 1959, the Soviet Union possessed something the West didn't, a functioning ternary computer. About 50 units were manufactured and distributed to research institutions across the USSR. Students finally had access to computing hardware. Researchers could experiment with this new paradigm. For a brief moment, it seemed like ternary computing might actually become mainstream. Then reality intervened. The manufacturing facility had no interest in scaling up production. The Setun was quietly discontinued. It didn't fail because the technology didn't work. It failed because the Soviet Union lacked both the industrial ecosystem and the political will to push it forward. More fundamentally, it failed because the world had already chosen binary. Memory systems, transistor designs, software architectures, the entire computing stack had locked into two-state logic. Setun never really stood a chance against that established momentum, and it simply faded into obscurity. The technical challenge, nobody solved. Every computer chip today consists of tiny devices called transistors that switch between 2 states. A classical transistor operates by switching at a specific threshold level. You can think of this threshold like a person's patience level. Annoy them slightly and nothing happens. But cross that threshold and boom, you get a reaction. That's exactly how transistors work, and it's the foundation of binary logic behind all modern chips. A regular transistor has just one threshold level, but if you want to build a ternary computer, you need something fundamentally different. You need a device that can clearly distinguish between 3 separate states. How do you accomplish that? By giving a transistor 2 threshold levels instead of 1. That's the key to unlocking 3-state operation. From there, you can start building an entire computer using ternary logic. But that means rebuilding everything. All logic circuits, all memory systems, everything has to switch between 3 states instead of 2. That's an enormous amount of work, which is precisely why nobody seriously attempted it for decades after Setun disappeared. But now Huawei has released documentation for their new ternary chip built at 7 nanometer scale. The trick involves special transistors with 2 threshold levels instead of 1, allowing the chip to distinguish clearly between 3 different states. From that foundation, they've rebuilt all the fundamental building blocks, including logic gates and memory systems. A ternary memory cell can now store 3 values instead of 2, packing more information into less physical space. Let's make this concrete with one simple example, the AND gate. This takes us back to the original Setun computer, which also featured these gates. The AND gate is exceptionally simple but absolutely essential. Without AND gates, computers can't make decisions. Its function is straightforward. Only if all inputs are true does it output true. In binary logic with zeros and ones, it's simple, just 4 possible combinations. In ternary systems, things get significantly more interesting. Each input can be -1, 0, or +1. This creates 27 possible combinations. In this new setup, the AND gate returns the lowest value among its inputs. If you input +1 and +1, you get +1. If you input +1 and 0, you get 0. Anything involving -1 returns -1. With this simple example, you can see how each trit carries more information compared to binary bits, meaning higher information density. You can accomplish more with the same number of input connections, resulting in more compact chip circuits and more efficient designs overall. The position between digital and analog, ternary chips are still digital, but because they utilize 3 states, they occupy a middle ground between pure binary and analog systems. Digital chips are binary, just 2 states. Analog chips have infinite continuous states. Ternary chips sit precisely in between. This could represent a perfect compromise, but there's a significant catch: noise. A ternary device must distinguish between 3 different states, not just 2. Even the tiniest electrical noise or manufacturing imperfection can blur these states, causing errors. Building reliable 3-state logic at industrial scale is brutally difficult. And don't forget, today's entire semiconductor ecosystem is optimized for binary. Software, memory architectures, compilers, development tools, everything. That was the challenge in the 1950s, and fundamentally it hasn't disappeared. The material that could make it possible. The solution might lie in graphene and carbon nanotube transistors, one of the most powerful tools nature provides for electronics. These are microscopic rolled-up sheets of graphene just a few nanometers wide, and they're a perfect match for ternary logic because their physical size naturally determines how they switch. By adjusting the diameter of a carbon nanotube, you can precisely set 3 distinct logic levels. That makes them ideally suited for ternary computing, but the advantages extend far beyond that. Graphene itself conducts electricity incredibly efficiently, even at very low power levels. For any chip design, that translates to cooler processors, longer battery life, and substantial energy savings in data center environments. That's why TSMC and IMEC are investing heavily in graphene as one of the strongest candidates for post-silicon computing. And this isn't just theoretical research. A recent IEE paper demonstrated a ternary chip built with carbon nanotube transistors at 32 nanometer scale. The results showed 45% less physical area and 30% less energy consumption for identical AI operations that binary chips perform today. That's not an incremental improvement, that's a fundamental leap in efficiency. Why this matters now? So will ternary computing replace binary entirely? Probably not completely. More likely, it will find applications alongside binary for specific use cases where efficiency matters most. History demonstrates that the biggest revolutions in computing don't come from doing more of the same thing. They come from daring to try something entirely different. Brusensov's work was decades ahead of its time, but the industrial ecosystem wasn't ready. The entire computing infrastructure had already committed to binary logic. Now, with AI pushing energy consumption to unsustainable levels, with data centers straining power grids, with advanced manufacturing techniques finally available, the conditions might finally be right for ternary computing to get a second chance. Huawei's patent represents just the beginning. If they can demonstrate working chips at scale, if the efficiency gains hold up in real-world applications, this could trigger a fundamental rethinking of computer architecture, not replacing binary overnight, but creating a new category of specialized processors optimized for specific workloads where 3-state logic provides genuine advantages. The story of ternary computing is a reminder that technological progress isn't always linear. Sometimes the best path forward involves revisiting ideas that were abandoned, not because they were wrong, but because the timing wasn't right. Setun failed in 1959 not because ternary logic was inferior, but because the world wasn't ready for it. Now, 65 years later, we might finally be reaching the point where we need what Brusensov was trying to build, a more efficient foundation for computing that doesn't assume binary is the only option. The computing revolution might not come from making binary chips smaller and faster indefinitely. It might come from finally asking whether binary was the right choice all along.